Okay, I want to go over some problems that involve taking the inverse transform. These are some representative problems from the other textbook. I think they give a little better overview of the different type of problems that you might see. Um, so I've included them here for you to look at, the ones that I think are relevant. I've also included the solutions to the odd numbered problems so that you can practice. I do want you to note that on this problem 1529c, this function u of t should actually be u of t minus 1. So that's an error. This is actually why we don't use this particular textbook, is that even though I think in many ways their problems are better and his explanations are better, there are a ton of errors both in the solution set as well as just throughout the textbook. So that ends up being very frustrating for the students, and for that reason, we discontinued the use of this textbook and went with our current textbook, which is much less likely to have errors. All of the other time-shifted steps are correct in these answers. Just this first one on part C, this u of t should be u of t minus 1. So I'm going to work out a few of these problems similar to those shown, and in this I've included a lot of steps, but I haven't always included all of the steps. So, and the other thing is that you should check the work on this, because being only human, I can also make mistakes. So please do go through and check the work, see if you find any errors. If there are errors, they would likely be arithmetic errors or errors that I was just in a hurry and miswrote something. So the first thing I want to look at is problem 1526b. And I noticed as I went through here and worked this problem, after I got it all worked out, I noticed that I had used a cube in the denominator instead of the square, which is what you actually have in the problem. So this is the problem right here that you want to take the inverse transform of. Now, before I go any further, I want to say, first of all, the first thing you check is you make sure the polynomial in the numerator is of lower order than the polynomial in the denominator, and it is. The polynomial in the denominator would be fourth order if I were to multiply it all out, and the polynomial in the numerator is second order. So that tells me that it's okay to proceed with my expansion, partial fraction expansion. So here's what that would look like. And because I have s plus 2 cubed in the denominator, I have to include all three terms leading up to that. So I have an s plus 2, an s plus 2 squared, and an s plus 2 cubed. And if I multiply that all out, this is the equation that I get. Now, from this point, the solution becomes basically you want to, in this case, because you do have so many powers of s, you would want to multiply this all out and use the method of equating coefficients if you were going to solve this by hand. And the reason is because you have a cubic root here, you could pick s equals minus 1, you could pick s equals minus 2, then you'd have to pick two other values of s in order to solve for all four of the unknowns in the problem. But what I want to do here is use this as an example on how to use MATLAB. So the first thing I need to do is I need to input my function. So let's go back and look at that function again. So I have s squared minus 2s plus 4 in the numerator. Then in the denominator I have s plus 1 and s plus 2 cubed. So the first step is to input the numerator, and I input the coefficients in decreasing order. So this would be s squared minus 2s plus 4. And then this 1, 1 represents s plus 1, and 1, 2 represents s plus 2, but remember I have s plus 2 cubed. So the first thing I want to do is I want to multiply s plus 2 times s plus 2. And I actually do that using the convolve command. MATLAB understands that you are giving it transfer functions because MATLAB was originally, or that you're giving it Laplace domain functions. MATLAB was originally developed for controls applications. And so it has some very nice defaults where it understands and is very forgiving of things like this. But if you were to try to multiply denominator 2 times denominator 2, MATLAB is going to think you're trying to do matrix multiplication. So by using the convolve command, MATLAB understands you're actually multiplying functions in the S domain. So when I do the first multiplication, then I get the following coefficients. And then I need to do one more multiplication because it's actually cubed. So I take my original function times the function squared. So I do the convolve again. And so this would be the result of S plus 2 quantity cubed. Sorry about that. Go back. So this is a result of S plus 2 quantity cubed. I now need to take that and I need to multiply it by S plus 1, which I defined as denominator 1. And when I do that, these are my denominator coefficients. So if I were writing this out as a polynomial, this would be S to the 4th plus 7s cubed plus 18s squared plus 20s plus 8. And then I use the residue command. And I use the residue command with defining a matrix element here, RPK. And then I say residue of numerator and denominator, which are the values that I previously described. So what it then gives me back is it gives me R, which is actually the residues or the numerators. And it gives me P, which are the poles. And then it gives me K. And K is what happens if you have a numerator and denominator of equal order, or if the numerator is of higher order than the denominator. So MATLAB can actually be used to do a partial fraction expansion when you have a numerator of higher order than a denominator. It'll do the long division for you. Okay, so what you have to know about the way MATLAB works is it's going to give you the denominator poles in order with the numerator coefficients. And it's also going to give you the numerator coefficients when you have multiple roots. These poles are increasing in power. So the negative 7 is going to go with S plus 2. The negative 6 is going to go with S plus 2 squared. The negative 12 is going to go with S plus 2 cubed. And the 7 will go with S plus 1. So here that is written out. So the R's form the numerators. You notice we're increasing in exponent here, and the P's form the denominators. And in this case, K is 0 because our numerator was of lower order than our denominator. So this is your partial fraction expansion that you get when you plug in using MATLAB in order to determine the roots and the residues. So that makes it a lot easier than if you were to try to do all the mathematics, which would involve a lot of algebra. But remember, this denominator here is S minus the pole. So it's S minus a minus 2, which is why you have S plus 2. That's not true for the numerator because the numerator is just a value. But the denominator, it's S minus the root. So these negatives all become positives when I plug into the denominator. Okay, so now that I have that, I'm just going to take the inverse transform term by term. And so doing that, notice as I have successive powers here of S that I'm actually generating t squared in the time domain. So this is the result of taking the inverse transform. We always want to show that that is multiplied by the step function u of t. Okay, here's another problem from this particular resource. So in this case, I have the following that I want to take the inverse transform of. And so what I do is I break that into two parts, a over s plus 3, and then bs plus c over s squared plus 4s plus 5. So I should stop here and mention that the reason that we have this term the way we do is that s squared plus 4s plus 5 cannot be factored into real roots. So we're going to treat it as as completing the square so that we can get the right inverse transform. But before we do that, we still have to do our partial fraction expansion, which will give us a, b, and c. So multiplying out, and then Using the method of equating coefficients, I look on the left-hand side, s squared is multiplied by 1. On the right-hand side, I would have s squared times a, and I would have s squared times b. So 1 is a plus b. And continuing to do that for the s terms and for the constant terms, I find that I have a is equal to 5, c is equal to minus 8, and b is equal to minus 5. So I plug those in for a, b, and c, and then here is the function that I'll take the inverse transform of. So this first term will inverse transform easily, but I'll need to work a little bit on the second term. So the first thing that I've done here in this second line is to look at the denominator and to break apart this term 5 so that I have a complete square plus another constant term. So I can group these first three because I completed the square, and that would be s plus 2 quantity squared, and then I write plus 1. I now have the denominator looking like the damped sinusoidal function in the tables, and so now I have to figure out is it sine or cosine or both. So now I want to work on the numerator. If the inverse transform is sine, I would expect a 1 in the numerator. If it is cosine, I would expect an s plus 2. So if I look at minus 5s plus 8, I can basically change that 8 to a minus 10 and a plus 18. And the reason I want to do that is I can then factor out the negative 5, and that will give me s plus 2, and it'll give me 18. So the reason I want to do that is now this s plus 2 over the denominator is going to transform directly to cosine, and this 18 is going to transform directly into 18 times the sine. Both of those exponentially damped because it's s plus 2 and not just s. And then this first term is simply exponential decay. So here is what the function of time would look like. Now I want to go back, because one of the things that I like to ask on an exam is I'll give you a function like this, and I'll ask you, what would you expect the time domain function to look like? And so without really doing any algebra or any expansion, you can look and you can already see that you're going to have one term that's going to be an exponentially decay term in the time domain. And then you have another term that's going to be a damped sinusoidal function, because you can't factor this into real roots. So your answer would be, this would be the sum of exponential decay and an exponentially damped sinusoidal function. It's okay just to say sinusoidal, even though we have both sine and cosine, because as you know, we can take the sine and cosine and do a little bit of mathematics and get that to be just a cosine function. This is an equal sign in the video. I'll change that in the notes. It should be a negative sign, obviously. All right, well, what if we didn't want to, well, okay, let's just look at this problem, which is a slightly different problem. In this case, we have these exponential functions in the numerator. So a common mistake that students make is to try and take these exponential functions and somehow include them in the partial fraction expansion, and you cannot do that. You cannot do a partial fraction expansion on anything other than a polynomial. So what you have to realize is that this exponential represents a time shift. So we're going to pull it out of the function, do the partial fraction expansion on the function, and then when we take the inverse transform, we'll incorporate the time shift. So the first thing I've done here is to break this into the sum of the two numerator components on the same denominator. And then let's look at this function, which is common to both, and do a partial fraction expansion on that. So here's a place where I've omitted the steps. It's pretty easy to let s equal negative 2 and s equal negative 4. And if you do that, you get this result here for a and b. So the partial fraction expansion is shown in the square brackets here. And it's the same for both terms. The first of those terms being multiplied by e to the minus s, and the second by 4e to the minus 2s. So now when we take the inverse transform, both of these are exponential decays, one with a time constant of 1 over 4 and one with a time constant of 1 over 2. So we'll have e to the minus 4, but instead of t for this first term, because this has a coefficient of 1 on the s, we have t minus 1. And for the second set of terms, we have t minus 2. So when we take the inverse transform, it comes out to t minus 1 and t minus 2 respectively for these two terms. And then what I want you to note here is that on the step function, we have a u of t minus 1 and a u of t minus 2. And so the step function itself, when you take the inverse transform, is also time shifted. So I know that sometimes it's easy to forget to write the step function down, but in this particular case, it's very important because it's important that you show that this particular part of the function has a shifted start time of 1 second, and this has a shifted start time of 2. Okay, well here's the final example that I want to show in this particular set of videos. Here's an example where we have numerator and denominator of equal order. So the first thing that I've illustrated is if you're going to do long division, how you do that. So you take the numerator and you divide the denominator into the numerator. And so this first term, s squared will go into s squared one time. So I take 1 and I multiply by this. It comes down, I subtract it, and I get minus 6s minus 26. Now, this won't go into minus 6s any, so this is treated as a remainder. So basically, this is written in this form. So that's how you get to the point where you can now do partial fraction expansion. So I can't do anything with this 1, but I can now do a partial fraction expansion on this term. So the first thing I look at is, can this denominator be factored into real roots? And the answer is no. So instead of factoring into real roots, what I want to do is I want to do a completion of the square. And when I do that, I get s plus 5 quantity squared plus 1. And so in fact, I'm actually not going to have to do a partial fraction expansion because I can't really factor this down any farther than what it already is. So now I take this numerator and play with it a little bit. And let me change the 26 to 30 minus 4. Which means I can factor out a 6 and get my s plus 5 term, and I can move my 4 term over here. Looks like maybe, nope, this is positive, so I'm good. And then I take the inverse transform of each term by term. So the 1 is going to transform to del of t, and then the latter two terms will be exponentially damped, sine and cosine. Now here's a slide where I did this on MATLAB because I want to show you what happens when you try and do the same kind of problem and use the residue theorem. So here I've input that numerator and denominator, and then I've asked for residues, and notice I haven't done any long division. I've actually just input the numerator as s squared plus 4s, and the denominator is 1, 10, and 26. So s squared plus 10s plus 26. And then I've asked it for the residues in r, p, and k. So now if you look down here, you see this k is equal to 1. Okay, that's my first term that goes right here. And now once again, the p's are my poles, and the r's are my residues or my numerator terms, and they are matched. So the first r goes with the first p, the second r goes with the second p, and remember it's s minus p on both of these. Now, if you look here, okay, these are two first order terms with complex conjugate roots. And so you have this little table that comes from your book, and if you look at line 3, we have distinct complex conjugate pairs. And they're given in terms of a k, an alpha, and a beta. So let's go to the next slide. So here is my function again. And k, in this case, is minus 3 minus j2. And so k star would be minus 3 plus j2. Alpha is 5 and beta is 1. So the first thing I do is I find the magnitude of k. That's called for right here. So that's just the square root of 3 squared plus 2 squared, or 3.6. And then I find the phase, which is the inverse tangent of the imaginary part over the real part. And note, it is important to carry the sign with you, because if you don't, for example, negative 2 over negative 3 is going to give you the same result as 2 over 3. Only 2 over 3 will give you a positive angle, and negative 2 over negative 3 will give you an angle in the third quadrant. So it's important to at least be aware of what the signs are of your components when you take the inverse tangent so that you get the correct angle. So having done that, I now have k and theta. I know alpha and beta, so I can now plug those quantities into this formula shown in the table. So here is what my result would look like for the phase shifted cosine.